Welcome to the channel, everyone. In this video, I'm going to record myself analyzing this IB past paper. This is from the November 2019 exam series, and you can see this is a chemistry multiple choice paper. The answer here is already shown on the left-hand side, and it's now my job to explain to you guys why the correct answer is as such, and I'll try to also explain why some of the wrong answers are wrong in the process. So let's just jump right into the question. So the first question is about some more calculations, identifying limiting reagents and excess reagents. And for this kind of problem, I'd like to construct a rice table. Reaction, initial, change, and end, which some people reserve the use of this table for equilibrium mole calculation problems, but I find it quite useful to use this for calculating or determining which reagent is in excess and which reagent is getting used up, and also how much of certain products you are forming. The most important entry, I would say, is a change entry. The change numbers have to obey the mole ratio strictly. So for this particular question, you're given the number of moles of both starting reagents. If you just assume that you're going to use up all the HCl, mole ratio of 2:1 indicates that you have to use up 0.05 moles of CaCO3. And by calculating the final amounts, you can see that you have some CaCO3 remaining when you use up the HCl, indicating HCl is a limiting reagent. And you can use the same 2:1 ratio again to work out the number of moles of CaCO, to work out the number of moles of carbon dioxide, which is 0.05 moles. Therefore, the answer is C. Using this table also allows you to realize when you have made a wrong assumption, which you can quickly correct. So for example, if you just think that CaCO3 is a limiting reagent, and if you suggest that you use up all of that, using mole ratio indicates that you need to use up twice as many moles of HCl, namely 0.2 moles of HCl. We don't have enough HCl to begin with, and you end up having a deficit of chemicals, which can happen in economics maybe, not in chemistry. Anyways, the answer is C. Second question is about balancing an equation and then identifying the sum of all the coefficients. For equation balancing, what you want to do is to balance the high priority elements, which are the ones that show up exactly once on each side. It turns out everything except chlorine shows up exactly once on each side, so you can begin with you can begin with manganese, oxygen, hydrogen. Either is fine. Just leave chlorine until the end for this particular question. I choose to deal with manganese first. And I like to sneak the ones in because of two reasons. Number one, sneaking a one in indicates that you have already done addressing the balance of that particular species. Secondly, the ones are actually coefficients. So math, AIS, those students probably would not know what the coefficient is. So turns out these ones actually count. If you overlook the ones, you end up getting a different number. That would be the wrong answer. But let's continue balancing the rest of the equation, which should have a 2 in front of the water in order to balance the 2 oxygens from MnO2. You need 4 HCl to balance the 2 H2O. And I think by the end, the chlorine is already balanced. Therefore, the coefficients would have a sum of 1 plus 4 plus 1 plus 2 plus 1, which is 9. Answer is D. Okay, third question. Determining which sample has the greatest numbers of moles of oxygen atoms. Well, this what you can do is just to multiply everything up. Recognizing you've got 3 oxygens within a nitrate and you've got 2 nitrates within a formula unit of magnesium nitrate allows you to recognize that you need to multiply that 0.05 by 6. So you're looking at 0.3 moles of oxygen atom in the same, and the first sample, which happens to be the correct answer, because if you go through the similar kind of analysis, B 0.05 times 4 is 0.2, C is just 0.1, and then D is just 0.2. Therefore, A is the clear-cut correct answer. And this analysis also works if they're asking you for the number of oxygen atoms as opposed to number of moles. Comparing number of moles will give you the same result as comparing number of atoms, because the conversion only involves multiplying by Avogadro's constant, a process that's not going to affect the order of these numbers. Question 4 now is about identifying an s atomic orbital, and the answer is just A. So you guys should all recognize that s orbitals are spherical in shape. If you go to uni, then you recognize that some s orbitals have internal structures. A feature called radial node, but it's not required for IB, and it won't affect the overall shape anyways. B is actually an s orbital forming a sigma bond with some sp hybrid orbital. C meanwhile is a pure p orbital, and D will be a single bond, a sigma bond between two sp hybrids. Question 5, the correct answer is C, and this is a graph that you guys should be very familiar with. Further understanding that the drop as you go from S2 to S2P1 is because you are now going to kick an electron from the P sublevel, which is higher energy than an S sublevel electron. The other deviation from the general increasing trend has to do with you ionizing from P3. A P3 configuration has no unpaired electrons, while a P4 configuration has. The P3 configuration, everything is unpaired by that. And the P4, paired electrons will experience more repulsion, which makes it easier for you to kick. Like you only need to supply less energy because the internal repulsion will help you get the job done in kicking the electron. Question 6 is about general increase from left to right across period 2. And the answer to this question is B. First of all, A is wrong. Melting point shows no clear trend across the period, but there are different structure and bonding for the metals on the left-hand side and then the non-metals on the right-hand side. Electronegativity is an atomic property, and for this you only need to look at atomic properties, which are number 1, the number of shells, which is a controlled variable when you survey elements within the period. The other factor is the nuclear charge, which is basically the same thing as number of protons inside the nucleus. So more protons acting through the same number of inner shells results in the outer shell electrons, whether they are electrons within the atom or electrons that are already involved in bonding, to be more tightly held or tightly attracted to that particular nucleus. Therefore, B is the correct answer. For choice C, ionic radius commonly refers to the radii of the most common ion. So metals typically have small ionic radius, and non-metals typically have large ionic radius, because when metals form ions, they will end up losing what used to be the entire outer shell of electrons. However, between group 1 and group 2, for example, the group 2 ion will have a smaller radius than the group 1 ion, because they have the same number of electrons, but then the group 2 metal will typically have 1 extra proton compared to the group 1 atom that forms the ion. So again, question 6, the answer is B. Question 7 asks you to recognize an F block element, and for this you just need to recognize where the F block is. The F block is comprises of these 2 rows, and the samarium is the answer to question 7. Sc is scandium, and that's the first D block element. Sn is tin, and it's somewhere in the D block. Somewhere in the P block. S-style strontium is the group 2 element, so that's an S block element. Question 8, the effect of a stronger ligand. According to IB anyways, in reality, whether a ligand bonds strongly to a metal depends on many factors. Like some ligands prefer some metals, and there's no general trend. For IB purpose, however, you guys are just supposed to use the spectrochemical series. For this question, you don't need to use the actual series, but the idea is that stronger ligands will cause the D sublevel orbital to split with a larger splitting energy. Depending on the geometry, the D orbital will split into 2 or more energy levels. The splitting depending on the property of the ligand. Strong ligand in IB causes a larger DD splitting, which means that more energy is required to promote an electron from some lower level to some higher level. And then to cause a high energy transition, you need the atom to absorb short wavelength, because photon theory states that energy is inversely proportional to wavelength. Therefore, the answer is A. Question 9 involves identifying the shortest CO bond. Basically, you need to recognize the bond order of the CO bonds within each molecule. The higher the bond order, and bond order, basically a single bond has bond order 1, double bond order 2, triple bond order is 3. The higher the bond order, the shorter and stronger the bond. And if you have practiced enough, then you should recognize immediately that CO, carbon monoxide, is a molecule that has a triple CO bond. If you don't recognize it, then at least you can use some Lewis structure determination method to recognize that carbon has 4 valence electrons, oxygen has 6, so you have a total of 10 electrons to fill up the structure. And you typically give the bond is 2 electrons to form the single bond first, and then you have to distribute the remaining electrons. If you distribute them evenly, it turns out both oxygen and carbon are lacking an octet. And it turns out you need to move 4 more electrons for a total of 6 electrons to stay in the middle in order for the resulting structure to be satisfactory. So as you can see now, carbon monoxide has a triple CO triple bond, which is going to be the shortest. The other structures, the first compound is an aldehyde that has a carbon oxygen double bond. Carbon dioxide is got 2 carbon oxygen double bonds, and then the last compound is an ether, where both CO bonds are single. Therefore, the answer is B. Question 10 is about identifying resonance structures, and the definition for resonance structure, is that those are dot structures that represent the same molecule, but the double bonds are in different positions. And that's why the answer is A already. C, just by having a double bond, does not guarantee that resonance structures can occur. The dot structure should be able to allow double bonds to be positioned differently in the development of satisfactory Lewis structure, like something like ethene, which has a carbon-carbon double bond. There's no other reasonable way to reposition a double bond, because the carbon-hydrogen bonds can only be single bonds. Hydrogen is unable to form any double bonds. The Lewis structure is not correct. You need the Lewis structure to allow electron to undergo delocalization, which is so delocalization is what the electrons do, and the resonance structure is the result of electrons delocalizing within supercovalent molecules. And the choice B, bonds vibrating by absorbing infrared radiation, has to do with a phenomenon called resonance, which is unrelated to resonance structures. And resonance is more like a physics thing, where a molecule vibrates with the same frequency as the applied infrared frequency. Question 11 is about the structure and bonding in silicon dioxide. And you guys are just meant to recognize that silicon dioxide exists as a giant covalent structure, hence the answer is A. And what does the structure look like? You guys wonder. Well, turns out silicon dioxide has a structure similar to diamond, in which silicons are forming 4 bonds and oxygen forms 2 bonds. And you guys may wonder why silicon dioxide doesn't have the same structure as carbon dioxide. The best explanation to this has to do with bond enthalpy. Silicon and oxygen forms stronger single bonds than double bonds, in the sense that the silicon oxygen double bond is not twice as strong as a silicon oxygen single bond. So a lattice structure containing just single bonds throughout is more stable. Compared to carbon dioxide, the carbon oxygen double bond happens to be stronger than 2 carbon oxygen single bonds. As a result, forming molecules which have carbon oxygen double bonds happen to be the better option for carbon dioxide. They have never tested you on this explanation before, but in case you guys are wondering, there you go. So answer is A. Question 12, identifying sp2 hybridized atoms should be an easy task. The rule for identifying sp2 atoms is basically look at the number of electron domains around a particular atom. A 2-domain atom is always sp, 3-domain atoms sp2, 4-domain atoms sp3, and there's no exception to this rule. So back to this particular question. Well, that means that you still need to be able to determine the Lewis structures properly. The first compound, the aldehyde, the carbon is always sp2 hybridized, so that's the correct answer already. I'll just complete the other dot structures again. So the carbon within carbon dioxide are two domain atom, hence it is only sp hybridized. CH3NH2 may be a trap answer, but students should not overlook the lone pair on the nitrogen in deducing that the nitrogen is actually a 4-domain atom, hence it's an sp3 atom. Water, the oxygen is also a 4-domain atom, it's also a sp3 atom. 13, which atom does not obey the octet rule? The boron is a clear candidate that does not obey the octet rule, but they're asking for the fluorine, so that's a trap answer. The obvious answer is here is going to be sulfur, because the sulfur is clearly forming 6 bonds. And when you're forming 6 bonds, you have to have at least 12 electrons surrounding the central sulfur atom. The other common candidate, boron, because of complicated reasons, boron likes to form incomplete octets. They've never asked for the explanation on why boron forms incomplete octets on exams, but this is my take. I also teach A levels, and A level people have to know an idea called polarizing power. Boron does not form the octet. Boron can only form. Boron is okay in forming just 3 bonds and having 6 electrons surrounding itself. Okay, like the high electronegativity. Sorry, the low electronegativity of boron means that it doesn't really need to have like the full octet in order for it to be stable. At the same time, it doesn't form B3 plus either, despite the fact that B3 plus is isoelectronic to helium, which is a very stable noble gas. The problem with B3 plus is that the nuclear charge of the ion is too high, such that it will actually want to attract electrons that it has given away to the fluorine as fluorine becomes fluoride. But of course, fluoride is perfectly happy with the extra electron. So it turns out the solution to this instability is that boron would rather form a covalent bond with the non-metal atom. So instead of being an ionic compound, the fluorine actually forms a covalent bond with boron. Moving on, question 14 and 15 is about colorimetry experiments. Let me clear my screen first. Calculate the enthalpy of combustion of ethanol. I don't think you actually need the diagram in front, so let's just look at the answer. Answer choices, which the correct way to figure out the answer without the choices would be this: delta H C equals to negative Q divided by number of moles of substance burnt. Q itself is calculable using MC delta T. The mass in the numerator is actually the mass of the water. Typically, I don't recommend people using like eliminating the wrong answer to solve multiple choice problems. It's more important to be able to recognize the correct answer, because that actually saves you a lot of time. Of course, that means that you need to work really hard, like in understanding the theory. But in any event, the mass up there should be the mass of water, so we can rule this one out. Temperature change should not have the 273, because both initial and final temperatures are recorded in Celsius, and the difference in 1 degree Celsius is the same as the difference in 1 Kelvin. Therefore, the 273, the value of 273 should not be part of the solution. Between choice C and D, the extra factor of 1000 is present in choice C, and that happens to be relevant because the specific heat capacity gave the energy unit in joules, not kilojoules. The final energy unit, however, is in kilojoules. Therefore, you need to divide by this factor of 1000 in converting joules into kilojoules. Hence, the answer is C. Question 15, which quantity is likely to be the most inaccurate due to sources of error? For calorimetry experiments in the high school laboratory, heat loss to the surroundings is by far the most important source of uncertainty. It's very difficult to use like standard laboratory equipment to retain 100% of the energy released during an exothermic reaction and have it perfectly transferred to a body of water. The flame will heat up the surrounding air. The flame will heat up the test tube that contains the water, or beaker that contains the water. There's also incomplete combustion as well. All these will lead to the recorded temperature change being usually significantly lower than the theoretical temperature change. Like having an uncertainty of like 50% is actually not unheard of. But in any event, the answer is D. Question 60 is now about the enthalpy change of a reaction when they further give you supplementary information in terms of enthalpy of combustion. If you guys have revised, then you should remember that the delta HC of a reaction, sorry, my bad, the delta H of a reaction, not delta HC, delta H of a reaction in general can be determined by taking the enthalpy of combustion of the reactants and then subtracting it by the enthalpy of combustion of the products. So in this case, the answer should be -4163 as written, subtracted by the two other enthalpies of combustion, which themselves are negative. Therefore, you should end up adding the two. And the reason for this formula being valid is because of energy conservation. The energy change of a chemical reaction is independent of the path taken. So the imaginary path that we can take is two hypothetical reactions of first combusting the reactants to form oxides such as carbon dioxide and water. And then we can uncombust the oxides back into the product, which will not happen in real life, but then for energy determination, these like hypothetical reactions will have energy values that allow you to calculate the overall energy change that is valid. Therefore, the answer is C. Moving on, question 17, a pretty straightforward entropy question, which requires you to identify a change, a chemical change. That can be a physical change, but either way, a change that generates the most disorder by virtue of generating a lot of large number of moles of molecules in disordered state. So you typically will be looking at the increase in number of gaseous molecules. And choice B should be the answer. Choice A, you're actually reacting gas molecules to form a solid. There'll be a loss of disorder. So definitely not A. B and C both form gas molecules, but clearly B forms many more moles of gas molecules. You're making 5 moles of gas molecules as opposed to just 1 for choice C. Therefore, B should experience the greatest increase in entropy. Question 18 is about identifying the ion that has the most exothermic lattice enthalpy of hydration. The theory is that the more highly charged and the smaller the cation, the stronger the attractive forces between it and water molecules, which are polar and can undergo ion dipole attractions with the ions. The choices involve two group 1 ions and two group 2 ions. So clearly, calcium and magnesium should have more exothermic enthalpies of hydration. Within magnesium and calcium, magnesium is smaller. So magnesium should have a more exothermic enthalpy of hydration than calcium. So the answer should be C. Okay, question 19 is about analyzing monitoring graphs when you have when you're trying to study the rate of reaction. When the reaction is performed under two different settings. You have an old reaction, and the new situation involves doubling of the concentration of a reactant. Doubling the concentration will increase the rate of a reaction according to collision theory. Doubling the concentration may also result in the production of more products, as long as the species whose concentration is doubled is still the limiting reactant, which is indeed the case here, because the question says that you have an excess of calcium carbonate while like increasing the concentration of acid. Increasing the concentration of the acid will also increase the number of moles, because moles equal to conc times volume. And clearly having the same volume of hydrochloric acid is also essential. It's an essential consideration for this question. So overall, the rate increases as evidenced by a steeper graph, so it has to be C or D. And then the volume should also double because of moles. Therefore, the answer is D. Question 20 is a standard Maxwell-Boltzmann energy distribution curve. And when you heat a gas, the graph will undergo a shift towards the right, the peak shifting towards the right and decreasing, while the total area enclosed under the curve remains constant. And the best description, the best choice that satisfies the description should be the maximum is lower and to the right. So choice C is correct. Question 21 is about analyzing the unit of rate constant, as well as understanding how rate constant is affected by temperature. Rate constant is not affected by concentration, but it is affected by temperature, according to the Arrhenius equation, which is actually what the next question is about. Here, we just need to recognize that increasing temperature will increase the rate constant. The unit of a second order rate constant, meanwhile, can be figured out by using dimensional analysis. And you should write out a general rate law for a general second order reaction and recognize that the unit for rate is this, mole per dm cube per second. And then the square of the unit of concentration should be mole square dm minus 6. And if you group all the units, the final answer should be mole negative 1 dm positive 3 and then s minus 1. Therefore, choice B is correct. Question 22 is about analyzing the logged form of a Arrhenius equation. This equation is already in the form of y equals to m, and then 1 over t can be regarded to be the x. Then A meanwhile is c, and that's a minus f. Answer is A. Question 23, Le Chatelier's principle. The equilibrium constant itself is affected only by how the equation is written, as well as the temperature of the experiment or of the reaction. Increasing the temperature of an equilibrium system whose forward direction is exothermic. Well, increasing temperatures favor the endothermic direction. Therefore, you would expect to have fewer products, and accordingly, the Kc will decrease. Therefore, the answer is A. Changing pressure is not going to affect the Kc. Changing pressure will affect the number of moles, but it won't affect Kc. And that's just how, just how Le Chatelier's principle works. Question 24 has shown up a lot in past papers already. A system at equilibrium has maximum entropy and minimum Gibbs free energy because it's at this particular distribution of reactant and products. Well, this happens to be an equilibrium issue happens to have the most stable distribution of reactant and products, such that neither the forward and backward nor the backward direction is spontaneous. Answer is just B. Question 25, acid-base theory. The Bronsted-Lowry acid is a proton donor, and after a proton is donated, the base is the same as an acid, except that it doesn't have the H plus anymore. So the answer is going to be the proton, not the hydrogen atom, because the hydrogen atom implies that it's a H without the plus, or H with the electron, which means it does have the plus. But in the acid-base reaction, when the hydrogen is transferred, the electron is left behind. So the hydrogen atom that's transferred is actually a hydrogen ion, which is effectively just a proton, because the hydrogen atom typically does not have a neutron. Question 26. Amphiprotic species can act as both Bronsted-Lowry acid and base, depending on what you reacted with. The answer is D, because D is the only one that has a proton that can be donated under suitable conditions. They're trying to confuse you guys between the terms amphiprotic versus amphoteric, in which case the correct answer could be Al2O3 as well. The two middle species are just, everything else just wrong. 27, a species that can act as a Lewis acid but not a Bronsted-Lowry acid should be, the boron species should be the correct answer, because the boron atom within these covalent compounds are typically electron deficient. Boron typically only has 6 electrons within its outer shell within its compound, and this boron can form data covalent bond with a suitable Lewis base. And it's not a Bronsted-Lowry acid because it doesn't even have a hydrogen that can be donated as a proton. Therefore, 27 is A. Next question, 28, is about comparing the strengths of acids. The higher the Ka, the stronger the acid. Also, the lower the pKa, the stronger the acid. And the way to combine the two lists is to recognize that the pKa can be converted into Ka. It's 10 to the negative 4.8 and 10 to the negative 4.9 respectively. So clearly the chloroethanoic acid is the strongest. H3PO3 is by far the weakest. And then if you consider the two middle species, butanoic acid with the Ka of 10 to the negative 4.8 should be slightly stronger than propanoic acid, whose Ka is 10 to the negative 4.9. Because the more positive the power, the larger the value overall when you bring them as a power of 10. I don't think they care about that particular mathematical treatment anyways, because if you just look at the strongest and the weakest acid within the list, chloroethanoic acid has a lower pH already. And fortunately, they don't have a choice where the two middle acids are flipped in order and try to get you to look at the mathematical details. Moving on, question 29 is about calculating oxidation states. If you have done enough exercise, you should already be able to identify that the sulfur within SO3 2- has an oxidation state of +4. If you don't recognize immediately, well, hopefully you recognize the method. You've got 3 oxygen, which are typically 2-. So X plus -6 equals to -2, and -2 being the overall charge of the ion. And hopefully you don't need the GDC to work out that the value of X is 4. And if you repeat the same procedure for each of the choices, A, I think, is +2. B is +6. C, -2. And then the last one, it should be 0, by the way, because SOCO2 is an electrically neutral species. So SOCl2 is the correct answer. Question 30 is about identifying relative reactivity between different metals. So the idea is that a more reactive metal is able to displace a less reactive metal from the compound of the less reactive metal. So the first equation indicates that X is more reactive than Y. The last equation, meanwhile, or the second equation, meanwhile, indicates that Z is more reactive than X, because otherwise X should have been able to displace Z, but that's not the case. So Z is the most reactive, X is a middle child, and then Y least reactive. Therefore, the answer should be B. Okay, question 31. Products of aqueous electrolysis. The guidelines for determining the major product during aqueous electrolysis. Well, for the reduction reaction, which is what happens at the negative electrode or the cathode, you consult the reactivity series. It's basically the reverse. The less reactive the metal, the more likely that it's going to be displaced. It's going to be converted back into the elemental form. Sodium is a very reactive metal. It's way above hydrogen in the reactivity series. Hydrogen is not really a metal, but it can act like a metal in the sense that it can undergo displacement reactions or preferential reduction, which is going to happen in this case, because the hydrogen, which came from water, is actually 2H+ from water. That's a preferred reduction reaction. It's easier to achieve in terms of energy. Therefore, the answer is B over D. At the positive electrode, when you have a concentrated halide solution, typically the halogen will be the major product. And the answer is D. Question 32 is a difficult question. The theory is that the same number of electrons will be involved at each interface when you have circuit containing cells that are connected in series. And each electrode, again, experiences the same number of electrons. And what you should do is to complete the half equations for each reduction process. So silver reduction is a one electron process, while copper reduction and then hydrogen reduction happen to be two electron processes. So if the same number of moles of electrons is involved at each surface, let's say you have 1 mole of electrons involved, you end up forming 1 mole of silver, but only half a mole of copper and only half a mole of hydrogen. Therefore, the answer is B. Okay, moving on. Organic chemistry, which compound is not in the same homologous series as the others? You guys can try to recall the general formulas of some common homologous series. A, C, and D happen to be all alkanes. B has a different general formula. B satisfies CnH2n, which means that it's either an alkene or a cycloalkane, whereas the other ones all satisfy CnH2n plus 2. Therefore, the answer is B. Question 34. Reacting with a halogen by electrolytic substitution. Different kinds of hydrocarbons will undertake different mechanisms, which is a result of bonding and structure, but more like bonding itself. Alkanes, like or saturated compounds in general, can only undergo radical halogenation mechanism. Whereas A and B, having the pi electrons, will be able to undergo electrophilic mechanisms because the pi electrons allow the hydrocarbon to interact with something positive in surroundings. And you have to further recall that is benzene. Benzene rings are able to undergo substitution. The reaction mechanism is such that the halogen will add to a carbon atom at first. So one halogen atom will add to one carbon atom at first. And then one of the hydrogen atoms that was on the carbon will fall off. By completing a substitution reaction, you can actually retain, the benzene ring can actually retain this full ring of delocalized electrons, which confers extra stability. And that's what nature prefers. Nature likes compound to be stable. B being an alkene, cyclohexene is an alkene which will undergo electrophilic addition reaction with halogen. And you make dibromo or dichloro cyclohexane instead. Question 35 is about identifying a compound that cannot undergo addition polymerization. So the requirement for a compound being able to undergo addition polymerization is by possessing a real carbon-carbon double bond. The carbon-carbon double bonds within the benzene ring, however, are delocalized. They can't react like typical C double bonds do. So therefore, the answer is C. 36 is about SN mechanisms. SN1 is typically faster than SN2, and then you guys are supposed to recognize that tertiary halogen alkanes are the ones that prefer to undergo SN1 reactions. That's why the answer should be A or B. And I hope you guys can recognize that these are like tertiary hydrocarbon frameworks without having to draw them out. Between A and B, you have to recognize that CI bonds are weaker than CCl bonds and have a higher tendency to break during a chemical reaction. That's why the overall answer is B. As for why SN1 is faster than SN2, well, SN1 has slower geometry requirement. And SN1 is also preferred by tertiary halogen alkanes due to the positive inductive effect. Exactly why that's the case, you guys probably should revise your notes. And remember factors that lead to carbocations being more stable. For now, we'll just move on and look at the rest of the questions. So the next one asking about oxidation reduction reactions involving oxygenated organic compounds. The redox, I'll just show you my notes. The redox pathways involving alcohols, aldehydes, and carboxylic acids is as such. The old 2015 syllabus actually has one of these roadmaps within the syllabus. here this is a version that I made. You can see that alcohols can be converted into an aldehyde, which can be converted into carboxylic acid. To get an aldehyde, you probably have to perform the reverse of oxidation. So you have to begin with a carboxylic acid, which allows you to make an aldehyde. Turns out you won't be able to. None of the reagents that you come across with an IB allows you to stop at the aldehyde. You need to learn about some special metal hydrides, diisobutyl lithium hydride or something, if I remember correctly from my uni days. And that reagent allows you to reduce the carboxylic acid partially to become the aldehyde without further reducing the aldehyde. But in terms of the chemistry on paper, reduction of aldehyde requires you to begin with the carboxylic acid, which is a more oxidized compound to begin with. Therefore, the answer is C. Question 38. Optical activity is exhibited by chiral carbon atoms. Carbon atoms are chiral, in turn, by being bonded to 4 different atom groups. For this kind of question, you definitely should draw out the displaced formula for compounds whose structure is not too obvious, which means that you may actually need to draw out all 4. A has an implied carbon-carbon double bond. So this molecule can exhibit cis trans or either isomerism, but that's not the same thing as optical activity. B, the middle carbon looks suspicious, but if you fully draw it out, then you recognize that there's some symmetry within the middle carbon that prevents the middle carbon from considered chiral or being optically active. C, you've got 2 CH3s bonded to the central carbon, and when you've got two identical atom groups bonded to the central carbon, no, it's not going to be optically active. So the correct answer is D. So the third carbon on the chain is bonded to CH3, CH2, hydrogen, CH3, and Br. So 4 different atom groups. Therefore, the answer is D. Second last question. Uncertainty propagation. So when you have to add quantities that have uncertainties or subtract quantities that have uncertainties, so the treatments are the same, you have to simply add the absolute uncertainties. The absolute uncertainties in this case being 1.0 and 0.1. 1.0 plus 0.1 is 1.1. Therefore, the answer is D. Last question is about identifying the correct 1H NMR spectrum of tetramethylsilane. It's only got one type of protein environment, but more importantly, the chemical shift of these hydrogen atoms or these protons are defined to be 0.00 ppm. And that's why the answer is C. Hopefully the explanations make sense. Thank you for watching, and if I have time, then I'll try to go further back and do May 19. I may also do some other sciences, which hopefully you guys will find those useful as well in case you guys do 2 sciences. But thank you for watching. See you guys next time.